problems based on laws of set operations. So here we are going to perform few problems which are based upon the laws of set operations of part 2. So under this part 2, based upon this formula, that is, so we are going to deduce this condition, which is nothing but A minus B intersection C is equals to A minus B union A minus C under the advanced level. So here we are going to deduce that condition, or in other words, we are going to prove that condition. Then now under the advanced level, so in this advanced level, I say we are going to suppose the three sets, that is A, B and as well as C, in order to prove the condition which is A minus of B intersection C equals to A minus B union A minus C. Then now here the problem is of prove that A minus B intersection C is equals to A minus B union A minus C, where A comma B and as well as C are the subsets of universal set, that is mu. So here we are going to prove this condition, that is A minus of B intersection C is equals to A minus B union A minus C. Then now proof starts. So in our proof, say here as per the problem we have to prove, say here A minus, let A comma B and as well as C are three subsets of universal set, that is mu. Then now here to be proved condition is of A minus of B intersection C is equals to A minus B union A minus C. But here in order to prove this condition, so first of all we have to prove the two conditions, that is left hand side must be the subset of the right hand side and the right hand side must be the subset of left hand side, that is A minus of B intersection C must be the subset of A minus B union A minus C, and in the second case we have to prove A minus B union of A minus C as the subset of A minus of B intersection C. Then now in order to prove the condition, that is A minus of B intersection C is equals to A minus B union A minus C, we have to prove two conditions, those were of the first one as A minus of B intersection C, the subset of A minus B union A minus C, and the second condition is of the right hand side must be the subset to the left hand side, that is A minus B union A minus C must be the subset to A minus of B intersection C. Out of these two conditions, I want to prove the first condition, that is case number 1. So in our case number 1, I am going to prove A minus of B intersection C subset to A minus B union A minus C, that too by means of the element wise proof. So here in our element wise proof, we have to consider one element, that is x, which belongs to the left hand side. Let that element be x, let x belongs to the left hand side, that is A minus of B intersection C. That implies in its elaboration, say x belongs to the first set, that is A, but here since it is negative sign minus of this set B minus C, B intersection C, so here B intersection C is subtracted from this set A, therefore x belongs to this particularly only the set A, but it does not belong to this B intersection C. So here we can write it as x belongs to first set, that is A, since it is subtracted, so here and x does not belongs to this second set, that is B intersection C. Then now the next logical step will be of x belongs to A and is written as it is, but here I want to elaborate this condition within the floor brackets. X does not belongs to B intersection C can be written as X does not belongs to the first set, that is B. So here actually it is of B intersection C, intersection indicates and, whereas here since it is does not belongs to, if it is of belongs to, we would have written B and as well as C, but here instead it is of does not belongs to, therefore here instead of intersection we will be getting it as union. So here X does not belongs to B, so here instead of intersection I want to write it as union. The union symbolic notation is of V, so here or, then now X does not belongs to even C. Then now, so here the application, that is nothing but the A into B plus C. By means of the distributive property we can apply it as, so A into B first of all, then plus A into C later. So here A into B plus, then now A with C, that is A into C. So here we are applying the distributive property in this manner. So here when we apply this property, whereas in these sets, then now the next logical step will be off. That implies A with B, then later with A with C. That is the first bracket we are going to get as X belongs to A and X does not belongs to this B. Lower bracket goes. Then now here it is of or. Then now here in the second bracket X belongs to A and, so here X belongs to A and then the next one is of X does not belongs to C. Bracket close. Then now as per the definition, so here we can write the next logical step as X is belonging to A, present in A, and X is not present in B. So B is subtracted from A. So we can write it as X belongs to A. So here does not belongs, so we can subtract. So here B. So here B does not belongs, that is B is subtracted from A. In the similar manner or, then now here X belongs to A and X does not belongs to C can be written as X belongs to, so present in A and does not belongs to C. So here does not belongs to mean we have to subtract this particular C. Then now the next logical step will be off. So that implies, so it is the or in between, so it is the union of two sets. As per the definition of the union of two sets, we can write it as X belongs to the first set as A minus B. Instead of or we can write it as union, then the second set is of A minus C. So here we got this step by the definition of the union of two sets. Then now, so here LHS is of X belongs to A minus B intersection C, then we reach the RHS as X belongs to A minus B union A minus C. Then now, then the next logical step, then we have, so here X belongs to first set, that is A minus B intersection C, implies the right hand side is of X belongs to A minus B union A minus C. So from this it is clear that X is an element which is present in A minus B intersection C set, and the same element that is X is also present in the right hand side set, that is A minus B union A minus C. The elements which are present in the LHS are also the elements of the RHS, therefore the LHS will be the subset of RHS. From this it is clear that, so here A minus of B intersection C is the subset to the RHS, that is A minus B union A minus C. So in this manner we have proved the first case. So here let us assume or let us suppose this as the equation number 1 or the condition number 1. Then now let us go for the second case, that is case number 2. In case number 2 we have to prove in a reverse manner, that is right hand side must be the subset to left hand side. So your right hand side is of A minus B union A minus C, must be the subset to the left hand side, that is A minus of B intersection C. So here since we are going to prove it by means of the element wise, so we have to suppose one element, that is X. Let X is an element which belongs to the left hand side, that is A minus B union A minus C. Then now that implies, since it is of union or, so X belongs to first set, that is A minus B, or X belongs to the second set, that is A minus C. So here X belongs to, as per the definition of the union of two sets, we can write it as X belongs to first set, that is A minus B, then a union, that is R, the symbolic notation as V. Then now X even belongs to this second set, that is X belongs to this A minus C. Then now in the next logical step, so here that implies, so I want to elaborate the first condition, that is X belongs to A minus B within the brackets. Then now X belongs to this first set, that is A. Then now here minus B, B is removed from this A. So here X belongs to this only first set A, but it does not belong to this B. So here and X does not belongs to B, because here B is removed from the set A, or written as it is. Then now whereas here I want to elaborate X belongs to A minus C as X is present in A, but here C is removed, so X does not belong to the C. So here X belongs to the first set A and X does not belong to the second set, that is C. Then now here from these two conditions, so here up to this extent it is common. So X belongs to A and in the first set, and X belongs to A and in the second set is common. So here I want to take, X belongs to A and is taken as common. When it is taken as common, and in the bracket when up to this extent is taken as common, only X does not belongs to B is left over. Then now here the symbolic notation is of or. Then now X belongs to A and is taken outside as common, then now only X does not belongs to then now C is left over within the brackets. Then now the next logical step will be of, that implies x belongs to A, and whereas here x does not belongs to B or x does not belongs to C. So here x does not belongs to, say in case instead of does not belongs to here, and in case instead of does not belongs to here, if it is of belongs to and belongs to, we would have written say x belongs to B or C, that is B union C. But here it is of does not belongs to, so here the union, so here union becomes the intersection, so or becomes and here, so here B and becomes here intersection of that C. Then now the next logical step will be of, so that implies, so x is present in A and x is not present in B minus C, B intersection C, so x belongs to, so here A, but here it does not belongs to this second set. So here when it is does not belonging to the set, so here B intersection C will be removed. So here B intersection C is removed from A, because here it is x is not present, x does not belongs to B intersection C, therefore B intersection C is removed from set A. Then now from this it is clear that from left hand side x belongs to A minus B union A minus C, we reach the right hand side as x belongs to A minus of B intersection C. Then we have the next logical step, then we have x belongs to A minus B union A minus C, implies x belongs to A minus of B intersection C. So here from this it is clear that x is an element which is present in the LHS set, that is A minus B union A minus C, and the same element x is also present in this right hand side set, that is A minus of B intersection C. That means the elements which are present in the LHS set are also the elements of the RHS set, therefore LHS will be the subset of RHS. From this it is clear that we can write it as, so here A minus B union A minus C will be the subset to the RHS, that is A minus of B intersection C. So in this manner we have proved the second condition also. Then now let us assume, or let us suppose this as the equation number 2 or the condition number 2. Then now from two conditions, that is, or from two equations, that is from equations 1 and as well as 2, the first equation is of A minus B intersection C, the subset of A minus B union A minus C. So here this is our equation number 1 or the condition number 1. Then now the second one is of A minus B union A minus C is the subset to the LHS, that is A minus of B intersection C. And now this is our condition number 2 or the equation number 2. Then now from these two conditions it is clear that A minus of B intersection C is subset to A minus B union A minus C, and the right hand side, that is A minus B union A minus C, is the subset of A minus of B intersection C. That is LHS is the subset of RHS and RHS is again the subset of LHS. Therefore an LHS will be equals to RHS. That is, so here therefore we can write it as A minus of B intersection C will be equal to A minus B union A minus C. So in this manner we have proved this condition. So here hence it is proved.